Hello everyone, welcome to our YouTube channel. Today we are going to discuss about Bend's rule and energetics of hybridization. Bend's rule. Bend's rule helps us understand how atomic orbitals mix during hybridization and more importantly, how the substance around an atom influence whether a bond has more S character or a P character. The rule states that atomic S character concentrates in orbitals directed toward electropositive substituents, while a P character concentrates in orbitals directed toward electronegative substituents. Meaning, if a bond is formed with the electronegative atom, like fluorine or oxygen, the bond tends to use an orbital with the more p character. On other hand, bond with the electropositive group like hydrogen or a metals tends to use orbitals with more s character. Uh, Next, the reason for this, we know that uh, s orbital keep electron closer to the nucleus and are therefore lower in energy and are more stable. So if we bond to an electropositive atom which doesn't pull electrons very strongly, it is safer to use an s-rich orbital. But if we bond to a higher electronegative atom like a fluorine, it pulls strongly on the electron density. In that case, using a more diffuse p character orbital is favored. This balance explains the distribution of a hybrid orbital character in a molecule. Next is the example, that is of phosphorus pentafluoride. In this molecule, uh, trigonal pyramid, the molecule is trigonal pyramidal, and hybridization is sp3d. Here we have a two type of orbitals. First, axial orbitals, which are more p character, equatorial orbitals, which are more s rich. So, according to Bend's rule, the more electronegative substituents like a fluorine prefer p-rich orbital, so they occupy axial positions. If the substituents are mixed, say phosphorus halides, the less electronegative chlorine atom would prefer the equatorial s positions. Next is the Bend's rule, comparison to valence electron pair repulsion theory. We know that valence electron pair repulsion theory explains molecular geometry simply by saying that electron pairs repel each other and arrange themselves to minimize repulsions. However, Bent rule adds another thing. It tells us how orbital hybridization adjusts depending upon electronegativity. For example, bond rich in a p character are a tighter and occupy less angular volume, while S-rich bonds need more space and thus give larger bond angles. So Bent rule complements valence electron pair repulsion theory. It doesn't replace it, but makes our understanding more accurate. Next are the exceptions. For example, in the case of cyclic bromophosphate esters, bromine, which is a less electronegative, should ideally occupy an S-rich orbital, but experimentally bromine is found in a P-rich orbital because the PO double bond is very short and requires very short overlap, strong overlap. So it takes the S-rich orbital. Bromine with its large diffuse orbitals overlap poorly anyway, so it settles in a P-rich orbital. So we can like redefine Bent's rule like S character is used in strong covalent bond where overlap is good. P character is used in a weaker bonds where overlap is poor or electronegativity mismatch exists. Next are the applications of Bent's rule. It has a application in both inorganic and organic chemistry. Inorganic chemistry, it helps explain geometries of non-metal fluorides like SF4, PF5. In organic chemistry, it helps explain bond angles variations like fluoromethanes. It can also predict substituents' position in a trigonal bipyramidal molecule and explain differences in a bond lengths between axial and equatorial bonds. So Bent's rule is a powerful tool for explaining molecular structure. Lastly, is the energetics of hybridization. We know that hybridization is not just a simple mixing of orbitals. It actually involves energy changes. There are main three steps. First is the promotional energy. Like an electron is promoted from a lower orbital to the higher one to create half-filled orbitals that requires energy. For example, in a carbon, the ground state is 1s2, 2s2, 2p2. To form four bonds, for example, in a methane, one electron is promoted to make it 2s1 and 2p3. So that requires energy. Next is the hybridization energy, like a mixing of orbitals that requires energy. The s and p orbitals mix to form hybrid orbitals such as sp, sp2, sp3, etc. This step also costs some energy. Finally, the third step is bond formation energy. When new sigma bonds form, a large amount of energy is released. This release of energy is greater than the earlier costs and make the overall process energetically favorable. That is why hybridization happens naturally and it gives us a stable molecule with a strong sigma bonds. Thank you, and please subscribe to our YouTube channel for more such videos. Thank you.